In problems 2 and 8 from the problem set, we're going to talk about computing the principal nth root. And the principal nth root is just W0 in our computations, where we have to make sure we take the principal argument of our original complex number. So let's unravel that in these two examples. The z here is -1, and the argument of -1 is pi. We don't take negative pi, we take pi. And so for our fourth root, W0 is going to be the fourth root of the modulus of -1, which is 1 to the 1/4, which is still just 1. And then we're going to multiply that by cosine of the argument of -1 plus 2 pi times 0. And I'm not going to write 2 pi times 0. Divided by 4 plus I sine pi fourths. And so really it's just cosine pi fourths plus I sine pi fourths, which is √2/2 plus I √2/2. Okay? That's the principal nth root. And if we were to draw a picture, we would find the following. So here is that. The modulus of W0 is 1, so it's on a circle of radius 1. And our z, -1, is over here. And W0 is over here at √2/2 plus I √2/2. And by principle, you can sort of see if we take the angle for W0 and we add it, we sort of multiply with it 4 times, or add it to itself 4 times. Sorry, I got a little caught up there. Then we don't pass -1 when we do that. It sort of lines up exactly. So W0 occurs in between the positive real axis and z when we go around. And when we take powers of W0, we don't actually pass -1. So that's another way of thinking about the principal fourth root in this case. Now this one's the principal fourth root. But we can get the others, and the others are found by going, let's see, we're looking at fourth roots. So going around the circle, starting at W0, and stopping at every 2 pi over 4, or pi halves, or every 90 degrees. So W1 is going to be here, W2 is going to be here, and then W3 is going to be here. So you start off with one of the roots, in this case the principal fourth root, and then you go around the circle making marking points such that we get 4 equally spaced points. We're going to do a similar thing here. We're going to find the principal fifth root. Let me scroll down a little bit more. So again, here our argument, we saw this already in example 2, the argument of 1 plus I, the principal argument, is pi fourths, and the modulus of 1 plus I is √2. So then this tells us that our principal, let me even label it, the principal fifth root of 1 plus I is, it's the following. We're going to take √2 to the 1/5 power, and then cosine, where we use our principal argument, divided this time by 5. I should put, sorry, W0. I should put 2 pi times 0, but the 0 annihilates it. 0 is the great annihilator. 2 to the 1/2 to the 1/5 is 2 to the 1/10. And then we get cosine pi over 20 plus I sine pi over 20. Now we don't have to know exactly what the value is here, or even really approximate the value. What we can see, though, is that if we were to draw a circle now of radius 10th root of 2, very, very close to 1, then W0 is on that circle and makes an angle of pi over 20. pi is about 108, pi is 180 degrees. Pi over 20 is then, I think, 9 degrees. So it's very, very close to the positive real axis. And then the remaining points, I'm definitely going to mess up. But we're going to draw 5 equally spaced points around the circle. But again, here, this is the principal fifth root. And so the remaining points I'm probably going to mess up. I'm going to attempt to draw 5 equally spaced points. I think I've already messed up. Okay, there's an error here somewhere in this picture, sorry. These are, look how, these are very much not equal, but that's okay. But the point is you draw 5 equally spaced points. In fact, this is bothering me. I need to fix it. It's probably going to look more like this, I reckon. There we go. That makes me feel better. But nevertheless, these are the other ones, and we could compute exactly what they are in terms of polar form if we wanted to. But here's a geometric, sort of a geometric in quotes computation.